Boba, this room is a mess. You're supposed to clean it up. All you had to do was just put your toys away, move a couple of clothes into the bins, and you couldn't even do that before we recorded it. Look at me when I'm talking to you, son. All you had to do was clean the room. Why didn't you do it? Is it because you know that all natural processes tend toward disorder instead of organization, so that the effort of cleaning the room would be an input of work into a hopeless process, a battle against all of the natural forces of nature? Not only that, but that the energy that you used would be unavailable for work elsewhere, meaning that in wasting this, fighting a losing Sisyphean battle, you are merely accelerating the heat death of the universe? Is that why you didn't clean this room? No, because you a good boy. We aren't even mad about you in the second law of thermodynamics. Oh, hello, friends. If I look like I'm a mess, it's because I just spent a couple hours outside hanging up the Halloween decorations. I'll include a photo or two. Whew, it's sweaty out there, or at least I am. But that's okay. We all know that now that I'm indoors where it is cooler, the heat will leave me and go into the cooler air in the room. That's reliable. We can trust that. It would be very strange if I walked into a cold room and what heat there was in the room decided to suddenly descend upon me like a swarm of locusts. If I walk into a room that's 76 Fahrenheit, there's heat in the air. But you would never expect that heat to concentrate itself, force its way conductively into you, and cook you alive to boil your blood. That would never happen. Why doesn't that happen? Well, for the same reason the room doesn't clean itself, for the same reason a cracked egg never suddenly heals itself back up from its splattered mess. Time's directionality exists for a reason that has more to do with probability and statistics than it does with anything else. But when we use probability and statistics, i.e., mathematics, to describe how things work with observational evidence, that combo meal, we're doing physics. So, our last unit lesson on thermodynamics is about the second law of thermodynamics. Let's share the screen. All right, team, I want you to imagine a billiard ball. It has been lifted before we tune in. So at the point we tune in on this problem, you got to specify these things. Otherwise, Joe gets real upset trying to imagine what happened before the problem. But this thing is lifted above the ground. It has potential energy due to gravity because it has been lifted off of the ground before we tuned into the problem. And let's say that it's got 50 joules. It is released without being thrown up or down, which means that there is no extra work included in the release action. And we know this from last year. As it falls, thanks to the law of conservation of energy, or the first law of thermodynamics, if you want to call it that, this bad boy has to fall downward, and all of that potential will turn into kinetic. Now, we are going to assume that there is no air resistance. We could even say that we could assume that there's no air in the room. We're going to avoid any work being done on the billiard ball in this scenario. If there was air resistance, it would do negative work to slow it down as it fell, and that work would rob you of some of this kinetic energy. So we are trying to ignore those possibilities. So this describes what we can expect as long as there is no work required. Then the billiard ball strikes the floor, creating kind of a shock wave that shakes up its particles. And now those particles, severely jostled, are vibrating a bit more than they were before. The ball comes to rest, and that increased wiggle of its particles means that it has gained 50 joules of internal energy. So it's hotter. And we all know that all of this is completely possible, especially if you don't have atmosphere in the room, which there are plenty of places without atmosphere. The moon, those special chambers for training astronauts, other moons, a few planets, poorly decorated classrooms, very lacking in atmosphere. But you know what else would not require work? It would not require any outside work for this thermal energy to organize itself and lift this off the ground. If that positive 50 joules decided to turn into 50 joules of potential energy due to gravity, as long as this bad boy cooled off in the exact proportion, it would still balance. You would still have satisfied the law of conservation of energy. Yet, I want you to imagine that you're in the pool hall. You're at Peabody's on Dollar Beer Night. You and your buddies are throwing darts. You got the pool game going, and a billiard ball suddenly lifts itself off of the ground several feet. It develops frost on the outside of it because it has cooled itself off, and then it simply hangs there. The first law of thermodynamics may be very satisfied with this, but I imagine you would be quite disturbed. We know to expect that that should not happen. But if it is possible by the first law, but impossible due to the fact that we just know it's not possible, well, I guess we're going to need another law in order to make that one illegal. And therefore, we need a second law of thermodynamics. Sure, you could lift this up by doing external work, and no one would have any problem with that. If instead of lifting itself by just converting its own energy from thermal to mechanical, if you just go over there and you spend some of your energy to lift it, no one would bat a freaking eye. That's extremely normal and absolutely allowable. So the second law of thermodynamics is going to describe what processes are possible without external work. Now, that is not a definition. I'm just telling you what to expect this thing to be telling us about. If we zoom in a bit and we think about the quality of energy as opposed to the quantity of energy, which is what we were doing here. The quantity stayed the same, so therefore everything balanced out. But if we think about it in terms of the quality of the energy, what is going on to give it that energy? As the billiard ball is falling, all of its particles are moving in the same direction, downward. So I feel like it is fair to say that the kinetic energy of the ball is due to its particles all moving in the same direction, which, if you need the obvious spelled out for you, is downward. In other words, there's some organization here. Everyone is lined up and going in the same direction. Maybe not necessarily single file, but it would be hard to argue that this is not ordered. Everything is doing the same thing. That is a measure of orderliness, organization, like what Bo will not do for our room. When the billiard ball has struck the ground and its 50 joules are now an increase in internal energy, all the particles are still present and accounted for. But remember our descriptors of what's going on when you have heat added to something. Our collisions are in random directions, and therefore it is safe to say they're not very orderly. Or, in contrast to our previous one, this is disordered. And now we come up with a reasonable way of stating our expectations. You would not expect the billiard ball to lift itself off the ground and develop frost on it, even though that is quantitatively okay. It's not qualitatively okay. This feels right. We observe this happening constantly. But the opposite never happens. At least not without work being done. So while we don't have a way to forbid it quantitatively, what we can do is we can forbid it qualitatively. And it seems that the law should be that ordered energy and disordered energy only naturally move from one to the other in a singular direction. As in, this orderly to disorderly happens naturally. To go from disordered to ordered requires external work, i.e., it doesn't happen naturally. At least in an isolated system, it wouldn't happen naturally. In a system where you can borrow energy from your surroundings, all right, well, we'll add disorder over there in order to increase order over here. It still results in a net increase in disorder. And we'll start describing an isolated system. And that is one where its boundaries are not open to influence from its surroundings. So in an isolated system, if you were trying to get disordered energy to turn back into ordered, or thermal energy to turn into mechanical on its own, all of the particles would need to take those random wiggles, like left, right, up, down, left, right, up, down. Every single wiggle would have to, for at least an instant, be in the exact same direction. Now pick any number of grams, 0.69, 4.20, any number you like, 8,008 grams. Pick any substance you like, carbon dioxide, oxygen. Look up its molecular weight. How many moles per gram? Use some Avogadro number math. And for any amount of stuff, look at the number of particles in that sample. And if everyone is going in a random direction, it is not impossible for all of them to wiggle in the same direction if you get a certain frequency of wiggles, like 1,000 a second. But when you look at how large that number of particles is it likely No, in fact, it's so small that it is effectively zero. It is a possibility so remote that we can feel comfortable writing it off, especially the next instant they'd go back to random motion anyway. Or another way of thinking about it. Imagine you go over to somebody who is not me, because I'd be mad at you if you did this at my desk. You go over to some teacher who has a bunch of Batman figures on their desk. You grab up a handful of Batman figures and you toss them up in the air. What is more likely as the result of that toss? That every single Batman figure lands on its feet, upright, in perfect fighting pose, or that every Batman figure will land in some random orientation, most of them flat on the ground. Maybe one guy is kind of leaning slightly vertical because he plopped down on top of a couple other Batmen. Some of them are face up, some of them are face down. Obviously, the randomized orientation is much more likely. But we can think of this tendency toward randomness to be a statement of the second law of thermodynamics. It oversimplifies and it ain't quite right. But the second law does tell us that things tend toward entropy. And a really common colloquial way of talking about entropy is with disorder. Another one that you could do if you need like a visual of what's going on here. You got two buckets of ping pong balls. Each ping pong ball has a number on it. You start out with all of your ping pong balls. 1, 2, 3, 4, 5, 6, 7, 8. I'd suggest using closer to 20 for this. But every time you pull a random number from a random number generator, one of the balls goes into the other. So if you pull one, one goes in here. You pull 20, 20 goes in here. You pull 20 again, 20 goes back. Over and over and over and over. Is it possible that you could sort all of them into one? Just randomly? I guess on a long enough time span, maybe. Would it last for very many turns of the random number generation? Not at all. What would be the most likely state? Well, you could do this. Ping pong balls are cheap, feel free. But I will tell you that the most likely state that it tends toward is an even split. Statistically, the most likely state, the most probable state, is equilibrium. And we find that nature just pushes energy into this equilibrium because it is the most probable state. For the same reason that light seems to follow straight lines because they are the shortest paths or the least time taken. Heat seems to follow this probability principle. Things tend toward disorder. The term that is often used for this disorder is entropy. Now, the not overly simplified definition of entropy is that it is a measured thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work. Now, the simpler way that might be easier to wrap your head around, but again, it may be an oversimplification. And this leads to a bunch of the misunderstandings that people have about entropy, like those people who try to argue that the second law of thermodynamics precludes evolution by natural selection. Those people are fools. But a measure of disorder or randomness within a system. For some examples of high entropy and low entropy scenarios, let's take the billiard ball from the beginning. When did it have more disorder? Obviously, when it had hit the ground and heated up from that. It had gained those 50 joules of internal energy. When it was falling and had those kinetic joules, it had lower entropy. Notice that it went from the low entropy state to the high entropy state upon impact, which was natural. If you took organized Batman figures and threw them up in the air, the chances are that they would land in a random pile. Again, the low entropy ordered state is going to naturally tend toward the high entropy disordered state. And when we think about motion of particles, high energy and low energy, when do you have more randomness? When do you have less order? How does that correspond to temperature? Well, low entropy would be with cold objects. High entropy would be with hot ones because they have more random motion. Now we finally get to write a definition for the second law of thermodynamics. By spontaneous, I mean without external work being done. They can happen on their own without any external stuff required. Spontaneous processes in an isolated system. Remember, isolation means that the boundary between the system and its surroundings is impenetrable. It is well insulated, or maybe there just simply aren't surroundings because they aren't described in the problem. An isolated system is one where you don't have to worry about interaction between the surroundings and the set of objects, which is your system. Spontaneous processes in an isolated system increase the entropy of that system. Let's take, for example, one of those really nice coolers where you've got a low conductivity material and then between two layers of that low conductivity material, a vacuum. I guess air would work, but a vacuum is better. Because if you have a vacuum here, there's only one way for heat to travel across a vacuum, by radiation. And radiation is the least efficient, lowest wattage way to get heat transferred from place to place. Radiation, it's like a snail compared to the roadrunner of convection or conduction. So if you've ever wondered why those Yeti cups or whatever are so good at not letting temperature go, well, it's because there's not a lot going on in there. So let's take two objects. I don't care what they are, and neither do you. A 400 Kelvin thing and a 200 Kelvin thing. We know exactly what ought to happen. Collisions transfer heat back and sometimes forth. So we should fully expect that the result of spontaneous processes, because we are isolated from influencing this by the double layer with a vacuum cooler, the result of spontaneous process must be that they reach equilibrium. But when they have reached equilibrium, a really good way of thinking about equilibrium is it is high entropy because there are more places where the heat could be now. Before, the heat was in one place and it was going to the other. Here, heat can now move back and forth in equal amounts. So there are more places for it to go to. When you have more possible microstates, that is higher entropy. Thus, we would say that in this case, your entropy has increased. If you watch anyone else's YouTube videos on the second law of thermodynamics, you're going to hear microstates, and that's states of organization. Think about like the example with the two buckets full of ping pong balls. If one and two are in the left bucket, but the other 18 are in the right bucket, that is one possible microstate. And the microstate where all of the balls are in play that has the most possible places for change to occur would be equilibrium. Thus, it is the highest entropy state. I don't know how many of you have taken AP stats, but you might be a little bit grateful that on this one, this is a conceptual lesson. You're not having to do a bunch of that stats work. All right. What if the system is open? Well, that means that we have to worry about the surroundings. And in taking those into account, the entropy of the system could go up, the entropy of the surroundings could go up, or both could go up. And the second law would still be quite satisfied in any of those three scenarios. A moment ago, I mentioned the people who like to argue that the second law of thermodynamics disproves evolution by natural selection. Their argument is that since things tend toward greater and greater disorder, the increasing complexity of organisms can't be real because they should be getting less complex. There should be fewer organized structures, not more organization to the build. And that would be fine if the Earth was an isolated system. But the Earth has never been an isolated system. It's always been powered by the sun. So if there is an increase of organization in the system of the Earth, is there increased entropy somewhere else to satisfy it? And of course there is. The sun is burning through its nuclear fuel, turning hydrogen into helium. And there's your increase in entropy that is allowing for some enthalpy, some organization to happen here. Also, when you get to competition between organisms, you can use a lot of the same statistical math that underpins the second law of thermodynamics to describe like organisms get energy from their surroundings, and the most efficient ones are going to be the most successful. And it's some wild stuff. You could really get lost in some of the writings of Ludwig Boltzmann, and that's about as far back as I can think of people comparing evolution to thermodynamics. But I mean, they named a constant after the guy. Boltzmann's got to know what he's talking about. For a less heady example than the diversification of life on Earth, we can go back to the billiard ball from the beginning. Okay, so you could lift it, and it's already been heated up from impact. So we're tuning in at that point, where the example before has already occurred. It can't lift itself due to the second law saying that that is the wrong direction for the entropy to go in. But you could lift it yourself, and add in 50 joules of potential energy due to gravity. You could do that, but that required work from you. You robbed Peter to pay Paul. You might have increased the enthalpy, the orderliness here, but you decreased your own enthalpy, your own orderliness. Your entropy went up to reduce the amount of entropy here. So in order to give this the ability to do work back, you lost some of your own ability to do work. Again, robbing Peter to pay Paul. So what happened in you? Maybe your muscles grew hotter. Maybe you broke down glucose, which is a complex, low entropy, orderly molecule, and you broke it down into smaller molecules like carbon dioxide and water, and those have higher entropy. So again, the process trending from low to high entropy is still completely satisfied in this scenario. It just happened more to the surroundings than to this part of the system. But the system still had to pay its due in terms of obeying the second law. You can't win, you can't break even, and you can't leave the game. You will always lose, and entropy will always increase. You could, through incredible effort, force heat from a cold room into one particular object to heat it up. But that's going to require work. In fact, that's how a heat pump works. Like we have devices that do that, but in order to make that thing run, you've got to put in energy from somewhere else. So you might think, oh, I'm reversing entropy's direction in here. Time's basically running backwards. I'm violating all the laws. But no, it's just you're increasing the entropy somewhere else. So let's think about the consequences going on here. Consequences of the second law. And this one seems kind of screwy at first because it's like, wait, I thought hot objects had high entropy. So it's going from high entropy to low entropy. Well, you have to think of the system. The increase in entropy is greater for the cool object than the decrease is for the hot one. So this does still totally work. And again, this has more to do with the microstates at equilibrium thing. So heat flows from concentration to lower concentration. That directionality of transfer that we've talked about before is actually a consequence of the second law. Our second consequence of the second law: no heat engine, that is, no device that uses the motion of heat in order to do mechanical work, can ever be 100% efficient. We'll talk more about heat engines in only a moment, but this limitation is real and extremely impactful. In Florida, I think it is somewhere around 70% of our electricity is generated by the burning of natural gas. Locally in Tampa, I think it's more coal, but at least statewide, it's somewhere around 70% of our electricity is generated by the burning of natural gas. So the heat engines that work because of the heat from burning that natural gas cannot, by laws of physics, ever give you all of those joules of heat turning into all of those joules of electrical energy. There's always a loss. There is always a waste. And then, because of the directionality of these processes, you can never unburn it for free. So everything tends towards waste, and you can't undo it once it's been wasted. Really uplifting stuff, right? And finally, our third consequence. Mechanical energy and the other forms like nuclear energy or chemical energy will tend to convert or degrade into thermal energy over time, becoming unavailable for work. Think about this. Like you burn fuel in your car to get the engine to go, but not all of that heat is turning into work. Some of it is just causing the car to get warmer, or some of it is shaking the air, which you get as sound as first, but eventually it just settles to just the particles are wiggling and you've got more heat in the air now. All of that could have made your car go a little bit faster if it wasn't going to waste. Again, no heat engine can ever be 100% efficient, but all of this, even if it's just by the decay of the gas sitting in the tank, not even being burned, all energy tends to convert to thermal energy over time. You start a pendulum swinging, why doesn't it swing forever? Friction between the air where the string is tied. And what does friction turn your mechanical energy into? Thermal. So no pendulum can swing forever. No cycle is infinitely repeatable. If we apply all of this not just to energy, but to information theory, that's where you get some really depressing stuff, like using the second law of thermodynamics to explain why you age or why you can't keep copying your DNA over and over again forever without errors accumulating and cancer rates rising or something. But it will always tend toward that disorder, that degradation over time. Heat engines. Let's look at heat engines. Told you I would. And I don't want to leave you hanging like talking about pistons and not explaining what pistons are to Mary's satisfaction. So heat engines are machines energy from a hot reservoir to a cold reservoir, and in the middle, you use some of it to do mechanical work. Think about it like this. You got your hot reservoir, which is at a hot temperature, connected to your cold reservoir. And we know that it is absolutely reliable that heat wants to go from here to here. We understand that. We can use that. How do we use it? Well, if we have heat coming out of the hot and heat going into the cold, if we put something in the way that that moving heat can do work on, then we get a work output, and it's just the remainder that goes into here. That is to say that if you subtract the work done from the heat coming out of the hot reservoir, you get the amount of heat going into the cold reservoir. If these two numbers were exactly the same, this thing would be 100% efficient, right? If all of the heat went into here, then this should come out to zero, and this thing would be 100% efficient. But think about that for a moment. If you have just the hot reservoir and the thing doing the work, actually try to design that machine. Let's take the burning of coal at a TECO plant. Again, I'm sorry to trigger my environmentally conscious students. I know all of you are in those hippie butterfly clubs. But the simple fact is, at least here in the Tampa Bay region, coal is being burned. And hey, the manatees like the hot water. You really want to deprive them of that? Of course, we could also be using nuclear power, which generates steam as well. And we could give that to the manatees. And then it'd be really cool because the manatees would have like three eyes and like extra tumors and stuff. But anyway, you boil the water inside of your heat engine. The steam rises and spins a turbine. The spinning of the turbine turns a magnet inside a loop of wire, generating a useful voltage. So the work turns into electrical potential energy. But if you sealed this up, because here's obviously your hot reservoir, and then the atmosphere outside, unless you are collecting this and then dumping the steam into the nearby pond for the manatees. They like warm water. But if you were to just seal this up, what would happen? The air above the turbine would eventually get to the same temperature as the air below the turbine, and the thing just wouldn't work. You got to give the heat a direction to go in other than just randomly beating against the sides of its container. Otherwise, your heat engine won't function. So if you don't give the heat a reason to go, if you don't provide it a cold reservoir to tend toward, well, then the work can't get done in the first place. So the heat engine must be at least somewhat inefficient, or else it won't turn on. And the efficiency for these coal burning plants is about 40%, if you round up. Of course, there are devices that are called heat pumps. That's the ones that use electrical energy to move heat against this gradient, where you are taking the cold reservoir's heat and concentrating it. So technically, you're reducing enthalpy here, but reducing entropy here, but entropy somewhere else is going to have to go up. In fact, it's going to be going up here at the power plant. So heat pumps are kind of the opposite of a heat engine. But the sad fact of it is that the heat engine is used to power the heat pump. So like an air conditioner takes the heat from inside of your house and forces it outside. If you ever stand next to an AC, it is blowing out hot air. It has forced the heat out of your house, reducing the entropy of your home, but increasing the entropy of the outside surroundings, increasing the entropy at the power plant. Robbing Peter to pay Paul yet again. The second law of thermodynamics will get its due, and that's unavoidable. It just is what it is. Now, if you zoom out, where does Earth get the vast majority of its energy from? The sun. So you could think of yourself as a little heat pump. You could think of life on Earth as a heat pump, moving energy from place to place by doing work. But that's okay because the source for that energy is external. But its entropy is going up. Eventually the sun runs out of this fuel. Sun can't burn forever. Now, admittedly, there is a chance that it can go to some other fuel, and it will almost certainly start converting helium. After the hydrogen converts into helium, there's going to be the helium flash where it starts fusing helium, expands out. It will destroy the Earth in that process, but Mars will get warmer. But even the helium can't last forever. It converts into carbon, and then eventually you just have this gigantic ball of carbon that can't do anything. Except, of course, cool off very slowly. And then every other star has to do that. Eventually, the universe will tend to have its entropy go up. It's a depressing fact that we're eventually going to run out of star making stuff, and the universe is just going to get very, very cold as that heat gets distributed uniformly throughout all of the matter in the universe. Everything reaches thermal equilibrium, and there's so much stuff in space that it's going to be real cold. Also, with the universe expanding, well, we know what happens to the temperature of a gas as it expands. The universe will end cold, spread out, and unable to do any more mechanical work. Uplifting stuff. But I mean, we are still using the second law of thermodynamics and its consequences to explain things. We can muse about something billions of years in the future because we know the reliable patterns upon which things work. That's what good physics is. Physics doesn't owe it to you to always be fun. You're not always launching marbles off of a table and hitting a target spot on because mechanics just has this wonderful predictive power. Sometimes that wonderful predictive power means that you are finding out that the sun's going to burn out. Oh well. It won't do it for a long time. So it's still worth it to have children, grandchildren. You can fit a lot of generations into 14 billion years, guys. Don't worry about it. Just later. Robbing Peter to pay Paul kind of thing. Well, here's your moment of zen at the end of this. Boba, say goodbye to everybody. Say adios, children. Adios, children.